Okay, and so that's why I took the time to cut out little circles, and we have our own little battery going. Hopefully it'll do all the stuff. The first thing to know is that electrical current, letter I right there, it's the amount of charge that passes through the cross-section area of a medium per second. You know, whatever. Look, here's a river, and the current is the water flowing, right? Sorry, I like earth science. There's my river. And it has algae bloom. That's funny, maybe. But anyway, current is the amount of water that's going to pass a point over an amount of time. And electrical current is the same thing. It's the amount of electrons that are going to go past a point in a certain time. I saw you guys doing this in physics the other day, right? Y'all did this. Okay, good. So anyway, current is equal to the charge in coulombs. That's our friend from Coulomb's law. That's the same thing, guys. And divided by time. So, like I said, it's the amount of charge in or so I'm talking about electrons passing a point in a certain amount of time. And then this Faraday's constant. This is given to you in your formula sheet. The Faraday's constant is this bottom right-hand corner, and on here it has 96,485 versus 96,500. They're just rounding. Okay, so anyway, there's that, and that's just a nice formula. Don't you like nice formulas that you can fill things into? I'm a big fan of that. So let's go ahead and look at that a little bit more. Kind of give an example. How much charge passes through a cross-section of a wire that is carrying 0.987 amps of current for 12.3 minutes? Notice in the formula, if you just want to get your formula sheet out, if you look at the formula, the I equals Q divided by T, what is the unit for time? So guess what you're going to have to do? You're going to have to convert that to seconds. So let's just go ahead and do that first, okay? So 12.3 minutes, and then 1 minute is 60 seconds, and then when you do the math there, you get 738 seconds. Alright, so then we have a formula, and the formula was current in amperes or amps. And so now if I just go ahead, hey look, I'm just going to use this as like setup. I'm just going to be like equals that, and then I got the time. And so I can say 0.987 amps is equal to, I'll change it to what, I guess. I just need like a little bit more room. That's the story of my life. Is equal to, my seconds are going to go on the bottom, 738 seconds, and then on top, like I don't know the charge, so I'm going to leave that Q blank, and then you can just solve, right? So I'm just going to multiply both sides by 738 times 738, and then I'm going to multiply this side by 738 seconds, and when you do that, you should get 728 coulombs. And that's just a capital C. That's as bad as the math can get today. Yay, I can do a formula! You can also do this, you can do this with dimensional analysis, which, I mean, that's fine too, but if you got a formula, you might as well use it. I'll show you their dimensional analysis. Are we good on that first part? 728 was the coulombs. So, okay, and invisible ink. So let's look at the second part. How many moles of electrons pass through the cross section? So look back at your little Faraday's constant there. 1 mole of electrons is 96,485. Do you see where I'm seeing that? So if I want to find moles of electrons, 728 coulombs, I'm just going to put my coulombs on the bottom, and I have 96,000, and you can use that number. I'm just going to go 500 because, you know, it's up here. And then that's 1 mole of electrons. I have what I want in the top right-hand corner, right? So I'm done. And once I divide there, you get 0.00755 moles of they don't, when they gave you the Faraday's constant on your paper, they didn't make it like a cute little fraction, but it says like per moles of electrons, and you guys know that per means divide, and that's a nice little fraction. But a lot of the conversions are given to you like with a fraction bar. This one they didn't. So don't let that trick you. That's the only thing I can think that might cause you problems. Are y'all okay with this? I like this. I'm good with this. So, I can try to show you how they did it. They did dimensional analysis, which I love dimensional analysis. I do dimensional analysis till I die, but if I had a formula, like I like that better. So they just did 12.3 minutes, and they converted it to seconds, and then they did coulombs per second, right? And so that gives you 728. So the amps, when you did your homework, I think I write that down like in a bubble, like coulombs is just amps per second, or amperes is coulombs per second. Like I think I wrote that down for you. So that's how to do it dimensional analysis style. You need to be able to go back and forth with that. That seems tricky, but if you look back at your formula, the I equals Q divided by T. That's Q, and that's T. Coulombs is the Q, and T is the seconds. So it's not anything you have to really remember. You just kind of can switch those out. Anyway, and then you take that, and that's what I did, and that's what we got. So, spontaneous redox reactions. If I were to stop what I'm doing right here, and I were just to put that zinc strip, if I put it in the copper solution, what will happen is this zinc right here is going to be oxidized, and the copper is going to be reduced. Can you look at this with me and be able to hang with me on that? How many electrons are getting transferred? 2. It's not always that easy. They use this one a lot because it is that easy. Sometimes you have to kind of pull apart the half reactions and bounce them. I'll be doing some of that today. So that's, and the reason for that, if we look at our reduction potentials, that big chart with all the little numbers for reduction, and it comes from positive numbers all the way down to negative numbers, and it's based off of the reduction potential of hydrogen being 0. If you look at that, which one of those would have a higher standard reduction potential? Which one's being reduced? The copper. So when we look, I think that chart is in this PowerPoint in a minute. When we look at that, copper should have the largest potential for being reduced. Like, that's what that chart means. The higher that number is, the more likely it is. It has better potential for being reduced. And so whatever gets produced in your reaction, that one has the highest reduction potential. Now that makes sense, right? And just because some of them are negative, that doesn't mean they can't be reduced. They're just less likely to be reduced than hydrogen, because hydrogen gets 0. And so that doesn't mean it can't happen. That just means that it's less than hydrogen. So anyway, how are we on that? I'm going to do a spontaneous redox reaction. I'll make a little Christmas tree for you. It goes in motion. Look, the two electrons pass from the zinc to the copper, and the copper gets reduced. The copper gets reduced because its charge goes up. Doesn't it go to 0? What did I say? The copper gets reduced because it goes down to 0.
Yeah, you said
I just like this. It makes me happy. What? Oh, I see it now. That's whatever. Okay. Anyway, so when you see solid metal placed in a solution containing metal ions, it's just, and if you see a change and see some kind of redox reaction happening, like a copper penny dropped in a solution of silver fluoride, I'm sorry. Do you see this? So I made a little copper Christmas tree, and I'm gonna put it in some. I have the silver up here. Where's my little Christmas tree? That's mine. You have yours? Okay. So, okay. Come see the thing. Oh, look. We made some iron oxide yesterday. soluble or if it was iron oxide. So what I actually did was I went and got the acid and I put it in there, and it should, if it was iron hydroxide is base, but it's a weak base. But if you put acid to it, the acid and the H in the acid and the hydroxide and the iron hydroxide should have made water, and then the iron should have made ions again, and not been like, you know, a precipitate. And that didn't happen. It's still rusty, gross looking, right? So anyway, I didn't know, and I tested it, and it worked. So I was like, yay, science. So it's definitely iron oxide, and I definitely can't like chemically fix that right now. I could drain it and like dry the precipitate. I could like filter it, and I could drain, and that can do something with a solid. There's a couple reactions you can do, like, but that's too much. Okay, so so here I just have some nothing, and I'm just gonna put some water in here. I want more water than that. You ever put the lid on that? They can get into that cause. I don't need to heat this, but. Where's the other Christmas tree? Give me that Christmas tree. Here's the Christmas tree I made. I like mine. Okay, so anyway, let's put our silver in there. This could totally not work, but it worked really well earlier. That's enough. It's really expensive. This is silver nitrate. So silver nitrate, I actually grabbed silver chloride even though it's not soluble. Remember, that's how you make a precipitate of silver chloride. Silver is very good. It's small, medium, large, make it what you want. Anyway, except for nitrate. So anyway, this is making, okay, it's all dissolved. That, I was like, maybe I heat it up because that helps, but it didn't dissolve. So, and I knew that. I was like, oh, wait, yeah, dissolve silver nitrate. So I'm going to put this in here, and the cool thing is, you see how that solution's blue? It started out clear, while it's blue. It's copper ions. Oh my god, those super fast. Oh! Here it is, everything! You just stand on the stool real quick. Wow. So if we just let it sit here, they should be all sparkly as usual. Can I have one? No. I'm so hot in it like I'm a little kid. I'm sorry. Here, I'm about to take Alright, so let's think about the chemistry of this. We had silver ions and we had solid copper. So now what do we have? Solid silver and copper ions. And the copper ions, tell me if I got a beer or not. Yes. I don't do that. It's beautiful until like it stopped working. It was beautiful when let me count these on. You believe me? So I guess that will turn blue, but if it doesn't, that's what sometimes happens. Okay, so anyway, so is the silver being reduced or oxidized? It goes from +1 to 0, so it's being reduced because the charge goes down. I like that. Yay. And so which it should have the highest standard reduction potential. See how I'm doing all that in my head? It's really hard, like you have to think your way through it, like talk to yourself. I don't understand why it would be a high. The highest reduction potential, it has the highest potential. Like if you have the highest academic potential, wouldn't you be like the best student? Yeah, and so if it has the highest reduction potential, then it's gonna be like gonna get reduced the most. Oh, you look at the chart. Oh yeah. Because if it didn't have a higher reduction potential, it wouldn't be getting reduced right now. I would put it in there and nothing will happen. Oh my gosh, it's really beautiful crystals. Really?
It's a Christmas miracle.
No, they're not. Bubbles look really close. Is this like the most beautiful thing you've ever seen? I had bought this stuff to do like silver coated Christmas like ornament balls, but if y'all like that better, we can just do this. It's much less Oh my gosh.
And the water is like a blue tint.
Oh, it is getting blue. It's getting blue. That means we probably need to pull it all out because it's going to end up sludge. Look.
Yeah, it really does. Yeah.
And pull it out, it's crazy.
These Twizzlers are not. Twizzlers. Oh.
Okay, so where is the fighting thing?
Please, my God, I'm sorry. Come back again.
Maybe I can try to do it really slowly. You just gotta say nice things to it, right? You just gotta say sweet things to it as you get it out, right? That'll work.
Honestly, though, what else would we do? If you leave it, maybe
Wait a little.
It's wrong with that.
So that's with the water.
Like right now? Let's just put it back and see how long we can do it. So if I touch this one, what's going to
Yeah, it's okay. Okay. Like, really close to it, like, soft.
Just take a picture of that and hang it on your What if I put it in here like this and was like, and then pulled it straight up out of there? But I love that, but like, let's just try that and see what happens.
It needs to be dipped without touching it. Use fish line, like drop it down in there.
I love you though. I don't think that will work.
Really solid.
Really solid.
It's already really solid. Look at all this beautiful silver though. Let's just like make it. You have no one to do with your target. So if we set it straight down in there. Okay, so if you set it down in there and pull it out.
Well, what if you didn't let it touch anything when you put it in there? It's kind of like.
So you're gonna take a picture and then we'll watch before I stir it up. Go ahead. Okay. Get some good scissors and cut that, and we'll try that later. Anybody, ready to go? I'll do it myself. Hey! We stopped farting. Screw around now. I mean, never mind.
We're gonna make Christmas trees.
And we're just gonna swirl it and sit it straight down in there and see what happens when we pull it out. We're learning things. We're making, look at this Christmas tree. How pretty it is. We're gonna hang it on Christmas tree. Isn't that beautiful? That's from silver.
Alright.
I look at turn blue though. Okay, we're just gonna sit this down in here. It's actually not working, so I'm just gonna sit it down in there. Okay, I'm just gonna sit it down in there. Okay, that's fine. And then we'll kind of see what happens. If we can pull it straight out, maybe that would be better. I really think this would be fun.
It looks like sparkly hot cream.
Maybe Catherine, do you want to?
I don't know.
What else in that?
I feel like it's all gonna fall in.
Yeah, they should call it off.
You need to put it back in there.
Yeah, don't take it out like that.
Take it out.
Shake it out. Silver.
Oh, well, the silver seat's already been reduced, so I can't make it an ion.
Unless you think it has a higher reduction temperature, right?
I don't know what that means.
You can look at the chart.
Let's look at the chart. We're gonna have a little.
I'll go do it.
Go do it.
No, just because it's very nothing.
Oh, nothing's higher than silver.
Oh.
um.
Well, we can melt it. We'll start melting it. Okay.
That one just looks like Alice's dress.
Shut up, dude!
Me versus you.
Oh, dang.
Oh. Wow.
Alright, well, let's just start with mine. Okay, so if you pull it straight out, everything's fine. Maybe, okay, let's try hers. It's gonna turn to sludge if we don't pull it off. You saw that. You saw it. I needed you to make like those little things. So I tried. Okay.
So, leave it in.
See, that's not pretty cool. Alright, we're doing this tomorrow. We're not making this small. Yeah, that's typical though.
That'll also reduce silver. Well, oxidize silver, my bad.
Yeah, we got it.
Oxide. It'll oxidize silver.
I'm surprised it didn't get cold.
Oh, wait, is permanganate deadly?
Yeah, it's
This
just
side
fine.
would be not
It's just
as
this, yeah, it's just this thing.
Yeah, so
we're
let's
good.
just clean it
Yeah,
up.
we can use that. We can use that.
Probably don't.
That's
And
like
then
the
we're
highest
just,
thing I saw.
and then make sure like there's a hook part secret out so we grab it.
But what if you use like, I was thinking, what if you use like fishing line or something like made it where you can just like angle it in there?
like hold it.
And where they wouldn't touch it, and you just pull it back out.
Yeah, we can, you can fix that look.
Yeah, like that. And then you can just pull it back out. That way they wouldn't touch it.
So we need some fish line and I got the hot metal. I got the stuff. You need some fish line.
I got fishing line.
Yep, probably should.
You can make the fish line?
Tomorrow?
I'm in my chemistry.
That's silver in here. We'll do some chemistry lab in lab tomorrow. We'll make this
Hey.
be okay.
That one looks pretty good.
Okay, so if it just hung there, that would be good idea. Okay, back to learning. Come on.
No more fun.
The video was.
Yeah.
I was learning.
Miss Raymond, permanganate.
We got some of that. We'll try in lab tomorrow. Whatever.
I'm making a chemistry. It's like
This one.
All of that is extremely expensive. That bottle of silver nitrate is $900. So yeah, it's gonna be that big. Hello. So let's go ahead and see if we can write this redox reaction. Let's kind of look at it real quick. Oh, we left that going that whole time. It's totally fine. Now here's the thing: is this balanced at all? No. And this is what they're gonna give you. They're gonna give you something like this, and you're gonna have to balance it, or they're gonna give you what's in that standard reduction chart, and then you're gonna have to work with that and make sure it's balanced. So let's go ahead and let's just kind of work on the whiteboard and see if we can split these up, get the right number of electrons, and then put them back together. This is the thing that you have to do, and it's so much worse than this in real chemistry. This is not bad, but if you have to do this when you go to college, like there'll be oxygens and waters and hydrogens and craziness. Anyway, I like those, but nobody else does. So let's go ahead and split up the reaction. Let's do the copper. So we can do the oxidation for copper, and we'll do the reduction for silver, and we'll do them separately. So let's do the silver. Not real low, but invisible thing again. So the silver is 1+. And so you have to kind of talk yourself through this, or you'll put your electrons on the wrong side. So the silver's charge, it goes from +1 to nothing, right? And so the silver, what it ends up doing is it gets, just give me a second, like I have to, the process that has to go through your head is kind of takes a second. So this gets reduced. So with reduction, I need to actually put the electron over there. Oh my goodness. Stop it. So anyway, I think I'm not screwing this up. I wrote it on my paper, but like I refuse to use it, right? Yeah. And then we have a solid. So it goes for, and don't forget your little. So there's your reduction. And then our oxidation. The copper is going to lose 2 electrons, right? And the reason it's going to be 2+ when it's done is because if you think about it, copper has a bunch of protons, like 29, but let's just pretend copper has 4 protons right now and 4 electrons. Can we do that? And that's a neutral copper atom. So, if it needs to be 2+, it loses 2 electrons. And so that's how you can think about it. So anyway, I can't subtract 2 electrons. So I have to add them to the other side. And that's good math, right? To move it to the other side to do the opposite operation. I mean, it's not. So anyway, so it's 2 electrons plus, and then you got your copper 2+, and now it's aqueous. Yeah, but now when you have redox, it's 2 sides of the same coin, right? And so if we are losing 2 electrons here, we're gaining 2 up there, and so we need to multiply that top reaction by 2, and then we'll add them together. And I'm just gonna like write that in another color below it. So I'm gonna have 2 silver ions plus 2 electrons, and that gives me 2 silver solid. Then I'm gonna add these up, and need to make sure that my electrons cancel, right? This whole theme of like playing the matching game, and when you have 2 things that match, you can pull them out of the deck. That always is the thing, and it always works. So my overall reaction is 2 silvers plus 1 copper, capital C copper. I hate the states. I've never had the states. I'm not into that. But 2 silvers and then 1 copper ion. And then everything should balance. Like I have the 2 electrons, but then the total number of silvers and the total number of copper should balance too. How we doing? I kind of made it a little messy right here. I'll fix that copper. It's not with me. Okay. And that's that. Yes. So what you do is you split your redox reaction into your reduction and your oxidation, and then you make sure your electrons are the same, and then you put it back together. And everything when you're done, everything, the charges should balance. What I mean by that is I have 2 pluses over here, and I have 2 pluses up here, right? And then your elements themselves, like 2 silvers, and 2 silvers, and then the coppers. If that ain't right, then you did something wrong. So they actually don't do that in this PowerPoint, but they have a whole PowerPoint for like that crazy kind that we don't have to do. So I mean, I know like I've spent a lot of time looking into exactly what you have to do, and this is what you have to do, and this is how they want you to do on the test. So if we go back to their little PowerPoint, I can show you how that's not. If we look at this, this ain't balanced. You know why? 2 plus sign, 1 minus sign. Excuse me, 2 plus signs and 1 plus sign. So it's not right. So you can tell that you didn't, or they didn't do it right. So that's how you can check. Anyway, so moving on. You're gonna get a lot of practice in with this. Now they put the 2, but where did those 2 come from? Just like magic, whatever. You gotta split it up, okay? Galvanic cells, they're always spontaneous, and so the electrons are gonna go through that wire, and the Gibbs free energy is gonna have to be negative. Remember, negative for heat and negative for free energy means that heat can be released and energy can be released, and so work can be done. In this case, if we're talking about Gibbs free energy, chemical energy is converted to electrical energy, and that's going to be the electrons moving through. We just did this a lot. We did this like 6 times today. But in case you missed it, here's your zinc and there's your copper. Like I said, the electrons travel through the wire. Your ions travel through the salt bridge. And what they have here is actually what's happening in our filter paper. It wasn't in the thing that we did today, but your zinc ions can travel through the salt bridge and they can come over here if they want to. And that's going to help bounce up the charge. It doesn't matter. It's not going to become part of the cathode. It's not going to do anything. So it's fine. And then your sulfate can go over here. As long as those ions don't make a precipitate in an aqueous solution, as long as it's not like some kind of crazy lead or silver, like those you'd have to be really careful of. But other ones, it doesn't matter. So that's not, usually in the salt bridge on the AP exam, they'll give you something like just sodium chloride or potassium chloride. But they can travel across the salt bridge. And they're doing that in mine, which is how it's still going, even though I just put a couple drops of the silver chloride on it yesterday. And you can tell because it's all blue and crazy. But it's still working and our voltage is still appropriate. So anyway, are y'all good on this whole process of what's happening with the electrons and all that? Okay. But here's a nice a little picture. Like I said, just make sure the electrons don't go through the salt bridge. And then your anode, anions, remember anions are negative because they have the N in them. And so the anions go toward the anode, and cations have a plus sign in. That's the T. I wasn't your chemistry teacher. That's the things I do in chemistry. Did I tell you that? Did I tell you those things with the plus sign? Anyway, so cations go toward the cathode. That's easy to remember. So lots of little tips for you. So on the anode, the reason the anode loses mass is not because the zincs go into thin air. They actually become aqueous, and so they're no longer solid metal. That's part of that bar. And the anode, the bar of metal, the actual bar of metal that's sitting there between Jacob and Jada, that bar of metal is called the anode, that piece of metal. And so the anode becomes lighter, not because it magically loses mass. It loses mass by the electrons have almost no mass. So they don't lose mass because they lose electrons. They lose mass because the zinc becomes aqueous and goes into solution. Apparently, like I read through, like I said, there's 3 of these, and I read the table leader, like question leader comments, like they released those to teachers. And students apparently thought that it lost mass because of electrons. That's not true because electrons don't weigh anything. And they also think that the electrons go through the salt bridge. So, but they lose mass because, like I said, that becomes aqueous. The cathode is going to gain mass because what ends up happening, if you think about it, the electrons are going to be right here, and so the copper is going to join right here with the other coppers because that's where the electrons are available. It's not going to become a solid and sink to the bottom because this is where the electrons are, and it just combines, right? So, how you doing? Okay. So the salt bridge, like I said, sodium, sulfate, nitrate, chlorine, chloride. Anything that doesn't make a precipitate is fine. It doesn't matter. And those aren't going to play a role in the redox reaction. They're just going to keep the half cells neutral. And if the half cells aren't neutral, the charge will build up and the reaction will stop. So, I didn't even read that, but that's, like I just said it. Go me. Anyway, so like I said, anions move toward the anode, cations move toward the cathode, and that's through the salt bridge. Whee! That piece of paper is working better than that $23 piece of glass I bought, which is hilarious. And I'm kind of sad because it's like, I'm going to do that. No, doesn't matter. Ooh, it moves.
Well, you just said like last time that you could show us that might
In the directions it just said to throw the solution in there. But we have some like silicon stuff that we could do. I don't know. I'm happy with my filter paper. I'm going to go with that next time. I don't want to send that back. Oh, this is so done. Look, I'm about to explain this without, like, there's 17 slides. I don't want it. Nope. I don't care. Do you know what, okay, if you want to know what the difference between, like, a volt and an amp is, like, come here, I need to make some coffee. I'll show you. I'm not going to make actual coffee, but I'm going to actually. I'm And voltage is like the push behind the every electron, right? And that doesn't change. That electrical potential isn't going to change. But the amount, as far as the amperage, the actual current, that I don't know. Is that John with your physics people stuff? We talk about what we call meter. How do you talk about it?
So voltage is force and amplitude.
Mhm.
Yeah, but then how I say is like voltage is push on the electron, current is how many
So what I'm saying is, if I make this, which I guess I turned it off, I did. If I make this big old cup of coffee, I'm gonna fill up my cup full. So if this water was electrical energy, like I would have more with this big cup. But the voltage is how far, as far as the push, the difference in like energy potential. So that doesn't change if I hit a little button or a big button. And so the voltage is that difference. And so it's gonna be how hard to push the electron to push through the wire. So that's not going to change if I hit the big button or little button. But the amperage, I will have more amps, more actual current. That can change. But the voltage, that difference in potential, that doesn't change. I guess not. But that's, so I thought about that the other day. I was making coffee. I was like, that's voltage. Okay. So anyway, you come back now. So in a 12-volt battery, the difference in potential energy between the anode and cathode is 12 joules per coulomb. Volt is joules per coulomb, by the way. I don't think you'll have to go back and forth between that, but that's what it is. 12 joules of potential energy is converted to kinetic energy that moves the electrons. Yeah. Voltage is energy per unit charge, or basically how hard each electron's getting pushed through the wire. All of these things are all voltage. And what you're going to see, the electromotive force, I think your book talked about that. That's voltage. But this is what we're going to be working with. We're going to be working with distill potential. And then remember when it has that little circle, that not sign, it's just at 25 degrees Celsius and 1 molar solutions, right? So anyway, these are all words for voltage. And I'm just looking at that difference in electrical potential. So anyway, I skipped a bunch of slides because they were when I have that little not symbol, that little zero symbol, now the current is being produced. No, I'm just kidding. But it's 1 molar for both of them, 1 to ATM and 25 degrees. And you know, my little galvanic cell that I've made here, it's voltage. Let's check it. 1.07. It should be 1.1. So that's pretty close. But is this room 25 degrees? Is it 1 ATM in here? Those were 1 molar solution, so I'm pretty impressed with that, right? I kind of feel like I feel kind of proud of myself. So anyway, it's working out. And I'll show you the math behind that. So the standard reduction potentials for half cell reactions are used to calculate the overall cell potential. And so the half potentials are going to be given to you. So this is the stuff in the chart. So the reduction potential for copper is 0.34 volts. Okay. And then the zinc one, I guess, is next. Oh, okay. Here they all are. So in there I have copper and I have zinc. And so the reduction potential for zinc is 0.76 volts, so it's negative. So in that cell right there, which one is being reduced, do you think? The copper, right? Because it has a higher reduction potential. And so the copper is getting reduced, and this is the reaction that's happening. The zinc is not getting reduced. The zinc is getting oxidized, right? So when I write that, I'm gonna have to reverse it. Yes.
So if you have like iron and copper, then would iron be the one that's getting reduced?
No, copper has the highest reduction potential, so has more potential to be reduced. So it's going to be the one getting reduced.
More so than iron.
No, you should use
Which iron, darling? This iron?
Yeah. 3 plus.
Yeah. So that one's going to get reduced. I was looking down here at this iron.
So then it would switch, and then copper would.
So copper would get oxidized in. So you would be making copper ions. So if we think back to this is exactly. So if we look back here, like this one's the one gaining mass, right? And so I'm making solid copper, and so the copper is it is getting reduced, and so that's what we expect because it's higher up on this reduction table than zinc. And so all these things are like real things that really happen. I need to get out more. Sorry. Anyway, and then you can like add arrows and all this. But in my mind, like I just think about it. I'm just like, okay, the bigger the reduction potential, like I just think about your potential as a student. Like if you have a lot of potential as a student, like you're probably gonna be a good student. So if you have a lot of reduction potential, like you're probably gonna get reduced. Like I just think about it like that. It just I don't know like a better way to tell you. So which species will be reduced? It's the one that has the most positive, least negative reduction potential, and it's going to be reduced. And so because it has the greatest ability to attract electrons, and as it attracts electrons, its charge is going to go down because electrons are negative, right? An electron can only decrease. So many emails. Sorry. An electron can only decrease its potential energy by moving to the thing with the highest reduction potential. So anyway, like you guys were saying, like could I put this with that and would it work? Well, you gotta look at the reduction potentials. I don't like this. I don't like this game. All right, look, I'm just gonna talk you through this, okay? People are like, you add it together, or sometimes people are like, oh, you can subtract that one and flip it. No. Nope. I was actually looking at a review book. It was last week, and I was like, okay. I was just making sure I was telling you the stuff that you had to know. I'm going to find this on my paper, and I'm just going to go to the white screen. Like, stop looking at this. Stop. Do you trust me? Maybe. Maybe I trust you, Miss Green. Anyway. Okay, I got it. Are we doing copper and nickel? Yeah. All right, I'm going to the other screen. Go with me. Go with me to the other side. So I have copper 2+, and I put those electrons in there. And so its reduction potential is plus 0.34 volts. And then I have this nickel. I have a nickel anode, so we can make us a little nickel battery. Nickels in batteries, right? Yeah, this is fun. Like I said, I need to get out more. And so I forgot something, didn't I? Are y'all okay if I write my electrons right here? Does that make you sad? I just forgot them. Sorry. So look at your paper. Just go with me. Think in your mind. Is that negative? Which one has a higher reduction potential? Which one has better potential to be reduced? Copper. So which one is actually going to be reduced? Copper. Cool. Great. Perfect. So this one's going to get reduced. So that's your reduction. And when I used to do these when I was in school this semester, last summer, whatever, I would write like my reduction over here. Because I like to get out like copies of paper and homework, you know. And then I would write my oxidation over here. This one's going to get oxidized, right? So when the one that's getting oxidized, when you go to write it, you're going to have to reverse it. Because if I go this way, I reduce the sign. Watch me. As I go this way, it increases. So this is oxidation. Do you see? Like, I don't like to memorize stuff. This formula ain't on that sheet, so you're going to have to understand it or like sit there and go like, do I subtract or minus? No. None of that is necessary. So anyway, I'm going to write my two half reactions. For me, I like this better. And so I'm going to write them out. I'm going to write the reduction as written. And so then I'm going to have to reverse the oxidation one. So I'm going to go nickel solid. And this is nice. I got the same amount of electrons. I'm into that. And it would be at this point in my life that I would take care of that. I got to multiply by 2 or 3 or whatever. Like I would do that here. Like if this only had 1 electron and that one had 2, I would multiply this and I would rewrite it. So that's handy. Anyway, so I see that everything's fine. It's all jiving. So now I can rewrite them together. And I see that my 2 electrons cancel. So I'm going to go ahead and take this out. That one's on product side. That one's on the reactant side. And now I can write my overall redox reaction. Now I'm going to check my charges to make sure I got 2 pluses and 2 pluses. I have 1 nickel, 1 copper, 1 copper. I'm done. Okay. Now, what is the electrical cell potential? I switched this little guy around, didn't I? So now this is positive 0.25. All you got to do now is just add them up. You just add them up. Like if this was enthalpy values and you do all the stuff you have to do to make stuff cancel, wouldn't you just add them all up when you combine reactions? Did I not just combine 2 reactions? That's what I just did, right? So now I'm just going to add them up. You get all your stuff straight, and then you add them up. And it's just like any other reaction with enthalpy or entropy or gives free energy. You do what you got to do. You reverse them, change it, whatever, and then you add them up. So my electrical cell potential is just going to be 5 plus 4 is 9, and 3 plus 2 is 5. And it's positive volts. And then that's or you could try to memorize that you need to write down the cathode and then the anode and subtract or minus. There's like 5 different ways that people teach this. I don't understand that. This is everything like we always did. You just get your crap straight and then add them up. I'm into that. Like I like that better. But if you're gonna do it a different way, Godspeed. How you like it? Is that okay? I hope that's right. I guess that's right. So oh, do you see what I'm talking about? Like subtract, minus, craziness. Some people will like just say to subtract it and then I can't even keep it straight. It doesn't make sense to me. Like the actual logical way of doing it makes sense to me. You do whatever you want. That's how I do it. And so we did get it right. It should be positive. If it's not positive, guess what you give free energy is? Positive, right? Because it's not going to be spontaneous. And then you're dealing with electrolysis. And so that's tomorrow's lesson. So determine the value of the standard cell potential for the voltaic cell working with silver and nickel. Do you guys want to get your little piece of paper out and click on this? I'll click up it on the board and you can look up if you want to. You want to try? Do you want me to just do it? Who wants me to just do one more? Who wants to try on their own? Alright, cool. It'll be up here. Look up if you want to. After this, I think I'm done talking, after this I'm done talking and you get to have the rest of the time to do a little practice. So, I've been talking a lot. This is the silver and the nickel, right? Cool.
So you only change the sign when it flips, but you don't multiply it by.
No, because the coffee doesn't fall from any farther. So
Because
the
one.
potential energy behind every single electron is not changing.
Because one.
Because the coffee doesn't fall from any farther. The twist behind each electron doesn't get any bigger.
When did you first get there?
I don't know the answer. I feel like that's right.
I thought you got 0.85.
I did it backwards.
You did it backwards?
So I just subtracted.
Okay. If you want to, whatever you want to do down here, you can do. But this, I like this. I like this. I like the things. I like the things. Just add them up. Add them up. Like everything else we've ever done, we change them so that they add up together right, and then we add the stuff up. We add the entropy up, we add the entropy up, we add the stuff up. And I like this better. You do whatever you want to, but I speak. Because like some of those little formulas are like subtracted, and then some of them are like reverse it and add it, and then no, I'm not doing that. This has not failed me yet, and it's right. So this is another one of those days where I'm just like, did we really just do that? Can I come over there? So this is it. This is all I have to teach you today. You got to do 1 through 10 on here. All of them. Godspeed. Get a piece of paper out. It's not that bad. I don't know how their answer key treats the redox reaction, but you need to make sure that your electrical charges are the same and your elements are the same. Okay? If you come across something weird, let me know. Get busy on those, and I will come around and check your homework, your lab thing. Listen, there's some homework I need to check. I know your test, but there was something from the other day. The pre-lab questions.
Yeah.
The pre-lab questions and your test from last time. Hang on, let me turn this record off.
Oh, you got it. I just barely.